Have you ever wondered whether the world you see is actually there when you're not looking at it? I mean, does reality exist on its own, or does it somehow depend on observation? Sounds like philosophy, right? But this question comes straight out of hard physics, and the answer is far stranger than common sense. In this video, we're going to unpack a beautifully simple idea that quietly turns our everyday picture of reality upside down, without equations and without hand-waving. Welcome to the channel, where we explore physics with curiosity, clarity, and a bit of playful thinking. Stay till the end, because the final insight is where everything clicks. And if you enjoy clear, curiosity-led explanations of the universe, make sure to subscribe. You won't want to miss what comes next. Let's start with a word we all use very confidently, even though we almost never stop to define it: reality. When you say something is real, what do you actually mean? You probably mean it's there, whether you're paying attention to it or not. A chair is real because it stays in the room when you leave. The moon is real because it keeps going around Earth, even if nobody looks up at night. That's a perfectly sensible, everyday idea of reality. And for most of history, physics agreed with it completely. Classical physics worked on a very comforting assumption. The universe is a collection of things with definite properties. Objects have positions, speeds, and paths. If you don't know them, that's just because you haven't measured carefully enough. Reality, in this view, is like a stage play already written. We might miss a few lines, but the script exists. Now here's the first uncomfortable question. How do we actually know something is real in physics? In daily life, we say something is real if we can see it, touch it, or bump into it. In physics, we're stricter and also more modest. We only talk about things that leave evidence. A particle is real not because we imagine it clearly, but because it produces a click in a detector, a streak in a cloud chamber, or a tiny flash of light on a screen. Already, something subtle has happened. Reality is no longer defined by what is, but by what happens. Here's a simple thought experiment. Imagine a tiny speck of dust floating in a dark room. Is it real if no light hits it? Common sense says yes, of course. But physics has to ask a sharper question. What could ever show us that it's there? Without interaction, without something bouncing off it, there is no experiment that can confirm its position at all. From a physical point of view, being real means being able to affect something else. That idea becomes crucial when we move to very small things like electrons. We tend to picture electrons as tiny balls flying around, because that's how we imagine reality. But when physicists actually do experiments, they never see a little ball. They see spots on a screen, patterns, statistics, outcomes. So what is the electron really doing between its creation and its detection? Physics gives a surprisingly honest answer. We don't describe what it is doing. We describe what it is likely to do if we measure it. That's not a philosophical dodge. It's a summary of experimental facts. Every successful prediction we make comes from that rule. At this point, it's tempting to say, reality must be hidden behind the scenes. But notice something important. Physics doesn't need that hidden picture to work. The laws describe relationships between observations with extraordinary accuracy, often more accurately than any mental image we invent. So the key shift is this. In physics, reality is not defined by our intuitive pictures. It's defined by consistent, testable behavior. That doesn't mean the universe is imaginary. It means our everyday idea of reality, solid objects with definite properties at all times, is an approximation that works beautifully at human scales and quietly breaks down when we look deeper. The real surprise isn't that reality is strange. The surprise is that the universe allows us to predict what will happen without telling us what's really going on in the way we expect. And that's where the real story begins. Let's take a very ordinary idea and see how badly it gets us into trouble. The idea of a path. If I throw a ball across the room, you have no problem imagining what happens. The ball leaves my hand, follows a smooth arc through the air, and lands on the floor. At every moment, it has a position and a speed. Even if you close your eyes halfway through, you still believe the ball has a definite path. That picture works so well that we hardly question it. Now let's try to use the same idea for something much smaller, say, an electron. At first, we expect the same story. The electron should leave a source, travel through space, and arrive at a detector along some tiny, precise route. We just can't see it because it's small, reasonable, sensible, completely wrong. Here's the experiment that forces us to rethink everything. Send electrons one at a time toward a screen with two narrow slits and place a detector behind it. You might think each electron goes through one slit or the other, like a microscopic bullet. But when you let the experiment run long enough, the electrons build up an interference pattern, a pattern that only makes sense if each electron somehow behaves like a wave and goes through both slits at once. Already, the idea of a single, well-defined path is in trouble. Now comes the really disturbing part. Suppose we decide to be clever and install a detector at the slits to see which slit the electron goes through. Surely that just reveals the path it always had, right? No. The moment we measure which slit the electron passes through, the interference pattern disappears. The electrons now behave exactly like little particles going through one slit or the other. Nothing about the electron source changed. Nothing about the screen changed. Only one thing changed. We asked a different question. So what was the electron doing before we looked? Physics gives a very precise but unintuitive answer. The electron does not have a definite path unless a measurement forces it to have one. Between measurements, the theory doesn't assign it a single trajectory. Instead, it assigns a collection of possible paths, each with a certain weight. When we calculate outcomes, we don't pick one path. We add up the contributions from all of them. If that sounds abstract, here's a useful analogy. Imagine planning a road trip. Before you decide, there are many possible routes you could take. You don't secretly drive all of them, but your final choice depends on considering them. Quantum physics works differently. Nature behaves as if all paths matter, until an observation pins down one result. The key mistake is thinking that measurement simply reveals a pre-existing fact. In quantum physics, measurement is an interaction. To find out which slit the electron went through, you have to disturb it, bounce light off it, shake it with a field, leave some trace. That interaction changes what can happen next. So the electron doesn't lose its path when we measure it. The path comes into existence because of the measurement. This is not a failure of our instruments or a temporary ignorance. It's a fundamental feature of how the world behaves at small scales. The equations predict the outcomes perfectly, but they refuse to tell us a comforting story in between. The lesson is sharp and a little unsettling. Paths belong to measurements, not to particles. Reality, at this level, is not a movie playing frame by frame behind the scenes. It's a set of possibilities that only crystallize into facts when something happens, when something is measured. And once you accept that, the rest of quantum strangeness starts to look less like nonsense and more like honesty. Let's talk about a word that makes people uneasy, especially when physics uses it: probability. In everyday life, probability usually means ignorance. If I say there's a 50% chance of rain tomorrow, what I really mean is that the atmosphere is doing something very complicated, and I don't have enough information to predict it exactly. In principle, if I knew the position and motion of every air molecule, I could calculate whether it will rain or not. The probability just reflects my lack of knowledge. For a long time, physicists assumed the same thing must be true everywhere. If something behaves randomly, it's only because we're missing details. Nature itself, we thought, must be running on clockwork underneath. Quantum physics refuses to cooperate with that idea. Consider a simple experiment. We fire identical electrons prepared in exactly the same way at a detector. We do everything as carefully as possible. Same energy, same setup, same conditions. Yet the electrons do not all land in the same place. They form a spread, a pattern that can be predicted precisely but only statistically. Now here's the key point. Nothing we can measure about the electrons beforehand allows us to predict where any single electron will land. There is no hidden tag we can read that says, this one will go left or that one will go right. We can only predict the distribution. At first, you might think this is just temporary ignorance. Maybe there are hidden variables we haven't discovered yet, some secret information that determines the outcome. But experiments have tested this idea very hard, and nature keeps giving the same answer. No hidden instruction set exists that reproduces the observed results without contradicting other measurements. In other words, the probability is not a confession of ignorance. It's a feature of how nature works. Here's a useful way to think about it. Imagine a perfectly fair coin flipped by a perfectly reliable machine. Even if you know everything about the coin and the machine, the outcome is still unpredictable in quantum physics. Not because you're missing information, but because the theory itself only assigns probabilities to results. But notice something subtle and important. The randomness is not sloppy. It's not chaotic. The probabilities follow strict mathematical rules, and those rules are astonishingly accurate. If the theory says an outcome happens 30% of the time, repeated experiments will agree with that number to remarkable precision. So nature is not undecided. It is precise about being imprecise. This leads to a deep shift in how we think about reality. Classical physics answers questions like, where is the particle right now? Quantum physics answers a different question. If I measure it, what outcomes can occur, and how often? Those probabilities are not predictions of what will happen in a single case. They are predictions of what does happen across many identical cases. And that's not a weakness. It's exactly what experiments confirm. You might be tempted to ask, but surely something definite is happening underneath all this randomness. Physics doesn't forbid you from asking that question, but it also doesn't need the answer. The entire structure of modern technology, from lasers to transistors, works perfectly by accepting probability as fundamental. So when quantum physics talks about probability, it's not shrugging its shoulders. It's being honest. It's saying the universe does not owe us certainty at the smallest scales. What it offers instead is something stranger and more reliable, a world where the rules are exact, the predictions are precise, and yet the individual outcomes are genuinely unpredictable. Once you stop treating probability as ignorance and start treating it as a law of nature, quantum physics stops sounding mystical and starts sounding refreshingly straightforward. Let's talk about something that makes people slightly uncomfortable, even though it works astonishingly well: mathematics. We have a deep desire to picture how things work. When we understand something, we like to imagine gears turning, waves rippling, or little objects moving along neat paths. A good mental picture feels like understanding. And for everyday life, that instinct serves us beautifully. But in fundamental physics, this instinct can mislead us. Here's a curious fact. Many of our best physical theories are easier to calculate than to imagine. The mathematics gives correct answers long before we can invent a picture that feels sensible. This is not a failure of imagination. It's a sign that nature is under no obligation to match the shapes our brains find comfortable. Take something simple: gravity. We often picture gravity as a force pulling objects together, like an invisible rope. That picture works well enough to throw a ball or launch a rocket. But when we look more carefully, gravity is better described as geometry, the curvature of space-time itself. Most people can't truly visualize curved space-time, but the equations predict the motion of planets, the bending of light, and even the ticking of clocks with extraordinary accuracy. The picture is fuzzy, the mathematics is sharp. The same thing happens in quantum physics, only more dramatically. People ask, is a particle a wave or a particle? The honest answer is, neither picture quite works. If you insist on choosing one, you'll be confused half the time. But if you use the mathematical rules for calculating probabilities, the predictions come out right every single time. Think of mathematics here as a set of instructions, not a photograph. It tells you what will happen if you perform an experiment, not what the universe looks like behind the scenes. When we try to force a picture onto the theory, we often add assumptions that aren't actually there. Here's an everyday analogy. Imagine trying to explain how a computer works by picturing tiny office workers inside, passing notes back and forth. It's a charming picture, but it quickly breaks down. The real understanding comes from logic and rules, operations that don't resemble anything human at all. The logic is real, even if the picture isn't. Quantum mechanics works the same way. The mathematical objects in the theory are not little physical waves sloshing through space. They are tools for calculating outcomes. When we treat them as literal pictures, we get paradoxes. When we treat them as rules, we get precision. Now, this leads to a subtle but important lesson. Understanding in physics does not always mean being able to visualize. It means being able to predict. If a mathematical structure consistently predicts experimental results, then it is telling us something real, even if our intuition lags behind. This doesn't mean pictures are useless. Good analogies can guide intuition and inspire insight, but they are scaffolding, not the building itself. When the scaffolding collapses, the building remains. So when people say, "I don't understand quantum physics because I can't picture it," the response is gentle but firm. You're not supposed to picture it. You're supposed to follow the logic, test the predictions, and trust the results. The universe is not obligated to be imaginable. It is only obligated to be consistent. And the remarkable thing, the truly stunning thing, is that a few lines of mathematics can capture patterns of reality more faithfully than any story we can tell ourselves. When we accept that, confusion gives way to clarity, and mystery turns into a deeper kind of understanding. Let's finish by clearing up a very common misunderstanding about what physics is trying to do. People often ask questions like, what is an electron really? Or what is reality made of at the deepest level? These are natural questions, and they come from a perfectly human desire for certainty. We want a final picture, a solid answer that tells us what the world is, once and for all. But physics, as it's actually practiced, plays a different game. At its core, physics is not a catalog of ultimate truths about existence. It's a method for describing what happens when the world is tested. When we say a theory is good, we don't mean it feels satisfying or philosophically complete. We mean it makes accurate predictions about experiments. Here's an everyday analogy. Suppose you want to understand how traffic flows through a city. You could ask, what is a traffic jam really? Or you could ask a more practical question. If I close this road, where will the cars go? Physics focuses on the second kind of question. It doesn't deny the first. It simply doesn't depend on it. Quantum physics takes this attitude very seriously. When we talk about particles, fields, or waves, we're using language as shorthand for patterns of behavior. An electron is something that, when placed in certain conditions, produces very specific, repeatable outcomes. That's not evasive, it's precise. This is why quantum theory often feels unsatisfying to people looking for a story. The theory tells you exactly how to calculate the probability of an outcome, but it refuses to say what the system is doing when no one is measuring it. Not because it's hiding something, but because that question has no experimental meaning. Consider this. If two different stories about what's really happening produce the same experimental predictions, physics has no way and no need to choose between them. Reality in physics is tied to consequences, not descriptions. This can feel like a letdown at first, but it's actually a kind of intellectual honesty. Instead of pretending to know more than experiments allow, physics draws a clear boundary. Beyond this point, words may wander, but predictions stay firm. And here's the surprising part. By giving up the demand to define what is, physics gains enormous power to predict what will happen. Technologies that shape our daily lives, semiconductors, lasers, magnetic resonance imaging, work not because we know what electrons are, but because we know how they behave under specific conditions. So when physics says it describes what happens, not what is, it's not avoiding reality. It's redefining it. Reality becomes the network of reliable relationships between actions and outcomes. This doesn't mean the universe is vague or unreal. It means our questions have to be carefully chosen. Ask the wrong kind of question, one that demands a picture where none is required, and you'll get confusion. Ask the right kind, one tied to measurement and prediction, and the answers are astonishingly clear. In the end, physics teaches a quiet but profound lesson. Understanding doesn't always come from knowing what something is. Sometimes it comes from knowing exactly how it behaves, and accepting that this may be the deepest knowledge we can have. And oddly enough, once you accept that limit, the world starts to make a great deal more sense. So what's the final answer to the question, is reality even real? The surprising lesson is this: reality doesn't disappear, but it's not built the way our intuition expects. At everyday scales, the world behaves solid and definite, and our common sense idea of reality works beautifully. But when we look deeper, physics asks us to be more careful. Particles don't carry fixed paths waiting to be revealed. Probability isn't a sign of ignorance. It's written into nature itself. And the most reliable descriptions of the universe aren't pictures we can visualize, but mathematical rules that predict outcomes with astonishing accuracy. Physics, in the end, doesn't promise a final story about what is. It offers something more honest and more powerful, a way to describe what happens when the universe is tested. Reality, from this perspective, is not a hidden stage play. It's the consistent pattern of results we observe when we interact with the world. And that's the real twist. The universe isn't unreal. It's just deeper, subtler, and far more interesting than our everyday intuition suggests. If you enjoyed exploring physics this way, clear, thoughtful, and driven by curiosity, consider subscribing to the channel. There's much more to uncover, and the best questions in science are always the ones that make us rethink what we thought we already knew.